Hello and welcome to our channel. Learn at 7:30 p.m. with your friend. Relations and Functions Part 3. Before watching this video, make sure that you have watched Part 2. In today's class, we'll discuss different types of relations. We know that there are different many types of relations, but in our class, we'll discuss three types of relations. Okay, in this chapter, we'll discuss three types of relations, and they are reflexive relation, symmetric relation, and transitive relation. Reflexive, symmetric, and transitive. Let us discuss one by one. First one is reflexive relation. Let's see the definition. A relation R on a non-empty set A is called reflexive if ordered pair AA in R, it belongs to R, for every A in A. So what is the meaning? So you know that to define a relation we need a non-empty set, and let R be the relation and let A be the non-empty set. Let R be a relation defined on A. That is, let R is a relation from A to A. Then R is said to be reflexive for every element of A. Let small a be an element of capital A. So, like this, it's a general element. Okay. So, for every element in A, ordered pair AA must be in R. Okay. Let us take an example. Let's set A is equal to 1, 2, and 3. Okay, this is not there. Let A equal to set 1, 2, 3. And let R is equal to 1, 1, 2, 2, and 3, say 2. And R2 is equal to, I'll take this as R1. R2 is equal to 1, 1, 2, 2, 3, 3. One more thing I'll take. R3 is equal to 1, 1, 2, 2, 3, 2, and 3, 3. Let us see which of these relations are reflexive. Let us consider the first one. Look at here, A is equal to set 1, 2, 3. And R1 is the relation set 1, 1, 2, 2, and 3, 2. So according to the definition, for every element in A, ordered pair A must be in R. So which are the ordered pairs that should be in R1? That is R1 is there, second element is here 2, so 2 is here, but what about 3? Here 3 2 is there, but 3 3 is not there. So what you can say about R1? R1 is not reflexive. And what is the reason? Since 3 3 not belongs to R1. So whenever you are writing, answering a question, you have to say whether it is reflexive or not with the reason. Let us see the next one. R2 is equal to set 1 1, ordered pair 1 1, 2 2, and 3 3. So what you can say about the second relation R2? It is reflexive because for every A in A, ordered pair AA belongs to R2. So here 1 1 is there, 2 2 is present, and 3 3 is also present. So you can say it is reflexive. It is reflexive. Since AA belongs to R2 for all A in A. And what about the last one, R3? 1 1 is here, 2 2 is here, 3 3 is here. So we do not bother whether any more element is there. Any more ordered pair is there. We will see whether AA belongs to R for all A in R. So according to the condition, 1 1 is present, 2 2 is present, 3 3 is present. Though there is an extra element, it doesn't matter. Clear? So in that case, R3 is also reflexive. Clear? So we'll come back to the definition. A relation R on a non-empty set A is called reflexive if ordered pair AA belongs to R for every for every A in A. Okay, moving on to the next topic, symmetric relation. Let us see the definition. A relation R on a non-empty set A is said to be symmetric if ordered pair AB in R implies BA in R. So look at this condition. Again, a relation is defined on a non-empty set A. Okay, and what is the condition for symmetry? If AB present in R, okay, if AB is an ordered pair in R, then this implies BA also must present in R. Then only you can say R is symmetric. For example, R is equal to 2, 3, 3, 2, 5, 1. Take this. This is a relation. So do you think that this is symmetric? See, 2, 3 is present. Then 3, 2. A, B, B, A. 2, 3 is there. 3, 2 is also there. 5, 1 is there. What about 1, 5? 1, 5 is not present. So what you can say? This relation R is not symmetric. R is not symmetric. Since 5, 1 is there, 5, 1 present in R, but 1, 5 is not an element of R. Clear? So if AB is present, BA must be in that relation. I mean, in that set. Then only you can say R is symmetric. So coming back to the definition, a relation R on a set A is said to be symmetric if AB is in R, implies BA in R. That's very clear. Moving on to the next point, that is called transitive relation. Transitivity. A relation R defined on a set A is said to be transitive if AB in R and BC in R. So there are two conditions. If AB belongs to R and starting with BC, BC belongs to R implies AC in R. AC belongs to R. Got it? So, if AB in R and BC in R, then there must be AC in R. Okay? If 1, 2 belongs to R and 2, 5 belongs to R, then what must be the condition? Then 1, 5 must be in R. Then only you can say R is transitive. Clear? So, according to the definition, what is reflexive? A relation R on a non-empty set A is called reflexive if AA belongs to R for every A in the given set A. For every A, AA must be in R. And about symmetry, if AB is present in R, then there must be BA in R. Then only you can say R is symmetric. And finally, transitive relation. A relation R defined on a non-empty set A is said to be transitive if AB in R and BC in R implies AC in R. Then only you can say R is transitive. Clear? And moving on to the next topic, equivalence relations. This is very, very important. Now, see the definition. A relation R on A. A must be a non-empty set. A relation R on a non-empty set A is said to be an equivalence relation if R is reflexive, symmetric, and transitive. R is equivalence relation if it is reflexive, symmetric, and transitive. If R obeys all these rules, then only you can say that it is an equivalence relation. Let us take an example. Let R is equal to, we need a non-empty set, isn't it? So 1, 2, 3. Okay. So let R is equal to 1, 1, 2, 2, 3, 3, 1, 2, 2, 1, then 1, 3, 3, 2, comma 3, 1. Let us check. I wrote many elements here. Let us check whether it is whether it is an equivalence relation. So first of all, A equal to 1, 2, 3. So yeah, 1, 1 here, 2, 2 here, 3, 3 here. 1, 1, 2, 2, 3, 3. So it is reflexive. What about symmetry? 1, 2, 2, 1. 1, 3, 3, 1. 3, 2, 3, 2. Where is 2, 3? 2, 3 is not there. So it is not symmetric. So let me include 2, 3 also here. Now let us see. Yeah, it is already checked that whether it is reflexive. It is reflexive. Now let us see the symmetric. 1, 2, 2, 1 is there. 2, 3, 3, 2 is there. Then 1, 3, 3, 1 is there. Okay. So for every AB, there is BA also present in R. So it is symmetric. Now transitive where we have to check. See, 2, 3 and 3, 2. Then 2, 2 must be there. Clear? Then 2, 3 and 3, 1. Then 2, 1 must be there. It is there. Okay. Now 1, 3, 3, 2. 1, 2 must be there. 1, 2 is there. Yeah. Nothing else. So 1, 3, 3, 1. 1, 1 must be there. So you can see that this particular relation is reflexive, symmetric, and transitive. Hence, you can say R is an equivalence relation. Let us take another example. You know the congruency of triangles. Okay, we have already learned congruency of triangles. So, how will you say whether a triangle is congruent or not? And we have studied so many points and so many, I mean, concepts about that. Okay, you know that every triangle is congruent to itself. Okay, every triangle is congruent to itself. Another one, if triangle 1 is congruent to triangle 2, you can say that triangle 2 is congruent to triangle 1. Okay. Then, if triangle 1 is congruent to triangle 2 and triangle 2 is congruent to triangle 3, then what you can say about triangle 1 and triangle 3? You can say that triangle 1 is congruent to triangle 3. So if you check, you can see that it is simply reflexive, symmetric, and transitive. Okay. So let us read the question here. Let R be the relation of congruency on the set of all triangles in a plane. Show that the relation R is an equivalence relation. So there is a given non-empty set A, and what is the speciality of the set? Set A is equal to all those triangles. Say, for example, I'll write triangle 1, triangle 2, etc. and such that each triangle, sorry, this is enough. Okay. Let A is a set of all triangles. And R is a relation. What is the relation? Congruency is a relation. Congruency is the relation, isn't it? Okay. Now, we have to show that the relation congruency is an equivalence relation. So how will you prove a relation is equivalence? We have to prove that it is reflexive, symmetric, and transitive. So first one is reflexive. This is the property that you have to check. So how will you write? Let triangle 1 belongs to A. Let triangle 1 belongs to A. So this is a general form. Okay. Like a general term we will take. Let triangle 1 belongs to A. Okay. Then triangle 1 is congruent to triangle 1. What is the reason? Every triangle is congruent to itself. That is the reason. Triangle 1 is congruent to triangle 1. Every triangle is congruent to itself. So what you can say? Triangle 1 belongs to A implies triangle 1 congruent to triangle 1. So this implies congruency. Our relation is congruency. R is reflexive. Clear? Now once again, let A be a non-empty set which contains set of triangles in a plane. And what is the given relation here? The given relation is equivalence. Equivalence is a relation. So we have to check whether R is reflexive, symmetric, or transitive. So first of all, let us check whether reflexive. Okay, let triangle 1 belongs to A. You know that every triangle is congruent to triangle 1. Otherwise, you can say triangle 1, comma, triangle 1 belongs to R. This is true for every triangle. Every triangle is every triangle is congruent to itself. If they are congruent, automatically it will come to the relation R. That is our condition. Okay, so triangle 1 belongs to R for all triangle 1 in A. For every triangle, this rule is satisfied. So you can say it is reflexive. And the second point is symmetric. Let us see. Let us take two triangles. Say triangle, let triangle 1 comma triangle 2 belongs to A. Now we are going to check the symmetry of this arc, whether it is symmetric or not. You know that triangle 1 is congruent to triangle 2. Let triangle 1 congruent to triangle 2. If triangle 1 congruent to triangle 2 means triangle 1 comma triangle 2 will be an ordered pair of R. Okay, this is a condition. Okay, now let look at here. Let's consider two triangles, say triangle 1 and triangle 2 in A. Now we know that triangle 1 is congruent to. Let us consider triangle 1 is congruent to triangle 2. If they are congruent, then definitely it will come to a relation. Now coming back here, if triangle 1 congruent to triangle 2 implies triangle 2 is congruent to triangle 1, isn't it? If they are congruent, what is the next step? Immediately you can say that triangle 2 and triangle 1 ordered pair is an element of R. This is true for all triangles that we will select from A. So if triangle 1 congruent to triangle 2 implies triangle 2 congruent to triangle 1. This implies R is, what is the relation here? Congruency. R is symmetric. Okay, let us check transitivity now. Third one is transitive. Transitive. Let us take three triangles, say triangle 1, triangle 2 and triangle 3 in A. Let triangle 1 congruent to triangle 2. Immediately you can say R is equal to first ordered pair is triangle 1 comma triangle 2. If they are congruent, immediately you can write in the relation. And let triangle 2 congruent to triangle 3. Immediately you can write triangle 2 comma triangle 3 is present here. Now let us come back here. Triangle 1 congruent to triangle 2 and triangle 2 congruent to triangle 3. Let me write like this. Triangle 1 congruent to triangle 2 which is congruent to triangle 3. So what you can say here? This implies triangle 1 is congruent to triangle 3. So immediately you can write triangle 1 comma triangle 3 in this ordered pair group. In this set R. So what you can see here, read this triangle 1 comma triangle 2 here, triangle 2 comma triangle 3 here, which implies triangle 1 comma triangle 3 is also present in R. So this implies R is transitive. So what you can say? Hence our R is reflexive, symmetric and transitive. Therefore, the relation R of congruency of triangles is an equivalence relation. So what is the conclusion? Hence R is an equivalence relation. This is how you have to do. Okay. So I hope it's clear for you. If you have any doubt, please share in the comment box or you can directly contact me and we'll meet with the next video and we'll do more problems on different types of relations. Okay. If you're watching this video for the first time, please subscribe and put the bell icon and kindly share the video with your friends. Thank you. Thanks for watching.